Hello, have you seen a weighing balance before? You put the stuff that you want to weigh here and then you adjust some weight along this scale until the balance is, well, balanced. This device uses the principle that the anti-clockwise moment is balanced by a clockwise moment, and from there you can measure the weight. So in this video we're going to talk about the current balance. What do we use the current balance for? We use it to weigh a magnetic field. For example, we may be interested to measure the magnetic flux density in the region between these two magnets. So let's set up our current balance. As you can see, there's an electrical circuit involved here. Next thing we do, we have to place this rectangular frame made of metal on these two razor blades. So you got to adjust left and right until the moments on the left and the moments on the right balance each other. Okay, so now you have managed to balance this frame on the razor blades. What you do next is to close the circuit. So the battery here will now pump a current this way and then this way and then back here. Alright, so this is the current loop. Let me just point out that there's no current flowing here because there's an insulator here. But actually this is not a very important point. Now if you don't do anything, this rectangular frame is going to rotate this way. Why? Because there's now a magnetic force acting on this segment of the frame here. I'm assuming that the direction of this magnetic field is such that it produces a downward magnetic force here. If it turns out the magnetic force is upward, what you do probably you want to switch the polarity of the battery here. So you want a downward magnetic force here that upsets the balance of this frame by trying to rotate it in an anti-clockwise manner. So to restore the balance, we will attach some weights on this segment of the frame so that the weight provides a clockwise moment. There are variations in the design of the current balance. Some people will use the rheostat to adjust the current until it's balanced. Some people will just add and subtract weights from here until it's balanced. Some people will put a weight along here and then just move left and right until it's balanced. Whatever it is, when it's balanced, we know that the moment caused by the magnetic force is balanced by the moment caused by the weights that we have added onto the frame. So now let's do the calculations. So this diagram is drawn looking this way, looking this way in the direction of SR. So in this view, we'll see the PS segment drawn here. So this is the PS segment. So in the calculation, you just write down this thing. So the anti-clockwise moment produced by the magnetic force is balanced by the clockwise moment caused by those weights that we have attached. So FB times this length L1 should be equals to W times this length L2. Do we know what is the magnetic force? Well, we can write it as BIL, where L is the length of the wire, right? The length of the wire that's sitting in the magnetic field. Make B the subject, and you got this expression here. Because we have the values for all these terms here, we can calculate the magnetic flux density. As you can see, the current balance is quite a crappy measuring instrument, isn't it? It's bulky, it's cumbersome to set up. The sensing element is actually the entire length of this wire, so we are not able to measure small changes in the magnetic flux density. Or maybe we have to assume that the magnetic flux density is constant throughout the length of the wire. Or maybe you want to say that it can only measure the average magnetic flux density along the wire. That's why nobody uses the current balance anymore. Nowadays we use this thing called the Hall probe. But then the current balance keeps appearing in your A-level examinations. That's why we're still talking about it today. Alright, that's all. Ta-ta!